Today we're going to be looking at adding and subtracting radicals. Yesterday we looked at turning radicals from entire radicals to mixed radicals and mixed radicals to entire radicals. And one thing we mentioned was that if I have two radicals, square root of 25 and square root of 16, the square root of 25 plus the square root of 16 is not equal to the square root of 25 plus 16. And that square root of 25 minus the square root of 16 is also not equal to the square root of 25 minus 16. Now, in this investigation, we're going to develop some of the rules that we're going to use for adding and subtracting radicals. And we're going to do that by looking at these values and trying to determine whether or not in our calculators these statements are true. So we're just circling the statements which are true, and we're going to cross out the statements which are false. Now, if I have 4 square root 3 and I add 5 square root 3, I want to know if this is going to equal 9 square root 6. And so in your calculator, you're going to get an irrational number like this, 15.58845727. And if I look at this 9 times square root 6, if this is a true statement, then they should equal one another, but they don't. So we're going to draw a line through that. Now, if we were to think about what is happening here, it's very similar to the statement up above. They've simply just added the radicals. And they've added the radicals, and in particular, they've added the radicands, the numbers that are inside the radical. So let's look at this next statement, number 2 here. So if I have 3 root 6 plus 5 root 6, is this the same thing as 8 root 6? So 3 times the square root of 6 plus 5 times the square root of 6, I get 19.59, which, if it is a true statement, should equal 8 root 6, and it does. So since it's true, I'm going to circle it. If I look at this next statement, 8 times the square root of 5 minus the square root of 5, does this equal 7 square root of 5? Well, 7 square root of 5, yes it does. Now, in this next example, I have 10 square root 11 minus 4 square root 5. And if I just walk through what they're doing, 10 minus 4, I get 6. 11 minus 5, I get 6. Now, we know from our examples up here that this is not how things work. So you can try putting this in the calculator to see if you get the same thing, but you will not. And if we look at the two statements that worked above, what we did, one thing that was true was my radicals were the same. And if you look at square root 6 and square root 6 here, they stayed as square root 6. And this 8 came from adding the coefficients 3 and 5. So let's look at this next example. I have 5 square root 7 minus 3 root 7 plus 7 root 7. And if I combine these values, it says that it should equal 9 square root 7. Well, let's see. 5 minus 3 is 2 plus 7 is 9, so that's true. And my radical remains the same, square root 7, true. And in this last example, I can tell you right away that's going to be false. For one, the indexes are different. I have an index of 3 here and an index of 2. We don't add the indexes. And even though I have this a coefficient that I've combined and the radicands are the same, because the indexes are different, that will be a false statement. So use the results in A to suggest a rule for adding and subtracting radicals. Now, when adding or subtracting radicals, only the number, and this number is the coefficient, is added or subtracted. So only the coefficient is added or subtracted. The radicand must be the same and must have the same index. So let's simplify these following questions down here. And we want to express the answer as a mixed radical. So 4 root 10 plus 10, well, if I have a number like this, that's actually a 1 there. That's 1 times square root 10. So this is going to result in 5 square root 10. And again, we're expressing these as mixed radicals. 5 root 3. Now we know that we're not doing anything with the radical. We're only subtracting this 2 from the 5. This is going to result in 3 root 3. 9 minus 4 minus 4. Well, 9 minus 4 is 5. Minus 4 is 1. We're left with just the square root of 2. Now in this example, I have 2 different radicals. So I have 8 root 6 and I have 2 root 6, which can be combined to be 10 square root 6. And then I have negative 4 root 5 and negative 4 root 5, which is going to result in negative 8 root 5. And that's as simplified as this question will get. Next, I have 10 root x plus 5 root x. Since the radical is the same, I can add these coefficients. 10 and 5 will result in 15 root x. And so what I'm doing is I'm only combining my coefficients. So if I combine these coefficients, they'll result in this new coefficient. If I combine these ones, they'll result in this combined coefficient. Same here, 9 minus 4, subtract 4, results in 1. 10 plus 5 resulted in 15. 3, subtract 5, I have negative 2. Subtract another one, I have negative 3. Negative 3 root 8. Now, in this example, use a calculator to verify that the following statements are true. So square root of 3 plus square root of 48 equals 5 root 3. So square root of 3 plus the square root of 48 is equal to 5 root 3. Well, let's see. 5 square root 3 is equal to 8.66. And yes, this is true. Secondly, I have 7 square root 8 minus 2 square root 50. And that equals 4 square root 2. And again, it's true. Now, with both of these, we have different values. So 3 and 48, and that results in 3. 8 and 50 resulted in a radicand of 2. Well, how does this work? Well, we can complete this by modifying this. So my entire radical, root 48, has the same radicand as the square root 3. Now, the square root of 48, we could express this as 16 times 3. So 16 times 3 is equal to 48. But I can write this as 3 plus 4 root 3. Square root of 16 is 4. And 1 plus 4 is 5 root 3. And so if I have different radicands, if I can simplify an entire radical to a mixed radical to get similar radicands, then I can simplify them into 5 root 3. So let's look at class example 1 and 2. I'm only going to I'll do this one, and then I'll do this one and this one. So if I'm writing my expression in terms of a single radical, I want to find my values that are going to simplify this into perfect squares. So 40, I'm going to choose 4 times 10 plus 9 times 10. This will leave me with 2 root 10 plus 3 root 10, and a final value of 5 root 10. If I have the square root of 96 minus the square root of 24, well, square root of 96 and 24 are both divisible by 8, so I can start with my 8s. And if we're looking for our perfect squares here, our closest perfect square, or our largest perfect square in 24 and in 96 is not going to be 8, but in this case is going to be 4. And so dividing 96 by 4, I'm going to end up with 4 times 24. And I can keep this the same. This will be 24. If I take out this 4, I'm going to be left with 2 root 24 minus 24. Now, if we think about 24 and 24, I could simplify it here, and I would just be left with root 24. But if we think about root 24, I can actually simplify this value a little more, and I could say, well, square root of 24 is the same thing as saying 4 times 6, or 2 root 6. With this last example, I'm looking for my common expression, my common radical. So 75, I have 25, that goes into 75, and it goes in there 3 times. And 48, I can pull a 3 out of, as well as 27. So let's see how we can do that. Well, first of all, I have 6, and then I have 25 times 3. I have 3, and I have 16 times 3, and I have 2, and I have 9 times 3. If I were to take out my perfect squares, I'm going to end up with 6 times 5 root 3 minus 3 times 4 root 3, and I'm going to have 2 times 3 root 3. If I combine these even more, then 6 times 5 is 30 root 3 minus 12 root 3 plus 6 root 3. If I combine 36 minus 12, I'm going to be left with 24 square root 3. All right, and actually this question down here is very similar to the above example, so we'll just leave off with this, and I'm going to go to the more challenging question, which is this worded problem. So the diagram shows the metal support, and this metal support is bolded. So these are my metal supports here. I call them X, X1, and X2. And so this is a bridge construction on the side of the hill, and the measurements are given to me in meters. So I know how high the bridge is, I know how long it is at each point, and what I'm wondering is how much metal is needed to actually build this bridge. So in order to determine this, what we need to do is find out my value for X1 and X2, but then we got to add those together. And we want to answer as a mixed radical in simplest form and as a decimal to the nearest tenth. So let's work with triangle number 1 and triangle number 2. And in order to find out what X1 is and what X2 is, we're going to have to use our Pythagorean theorem. So we know that a squared plus b squared, and this is for triangle 1, is equal to c squared. I know 4 squared plus 6 squared is equal to c squared. We have 16 plus 36 is equal to c squared, and 16 and 36 gives me 52 is equal to c squared. Now my value of c then is equal to square root of 52. If I solve for triangle 2. I have a squared plus b squared is equal to c squared. And I have 8 and 12, so 8 squared plus 12 squared is equal to c squared. 64 plus 144 is equal to c squared. So I have 8 and I have 208 is equal to c squared. So the next step of this process then is, and sorry if I want c here, is to combine our values, right? So I have the square root of 52 and I need to add the square root of 208. And so if I combine these values, and in order to combine them, I need to convert them into mixed radicals that have similar radicands. So I'm going to need to go x1 plus x2, and that's going to equal my total length. So x1 is my square root of 52 plus the square root of 208. Now, remember, in picking out a perfect square, we need to first find out what these numbers are divisible by. So I have square root of 52, and I'm not going to pull out any perfect squares out of that one. I have 2 and 26, but 208 is actually equal to 4 times 52. So 52 plus 2 root 52, and this equals 3 root 52. 3 times the square root of 52 is equal to 21.6. And this is in meters.